Welcome everyone to, let's see, I guess it's day 5, session 3 of our week-long virtual celebration of mind in honor of Martin Gardner. My name is Scott Borthman. I'm your host for this session and a member of the board, the Gathering for Gardner. We're very, very lucky and honored to be joined today by Matt Baker. Matt is a professor of mathematics at Georgia Tech, as well as an associate dean and an award-winning teacher. He's published 3 math books and over 40 research papers. He writes a popular mathematics blog, and he's a fellow of the American Mathematical Society. And I believe he's going to dazzle us with some magic tricks today. So without further ado, I give you Matt Baker.
Okay, thank you so much, Scott, for that introduction. So welcome. My name, as you heard, is Matt Baker, and I will be sharing some magic tricks with you this evening, and then explaining how some of them work anyway. But we're going to start with a little show and then go into a little more of a math/magic lecture. So I'd like to begin by going on a little rant, and I apologize in advance for this. I don't like to start with a rant, but I've just been kind of bugged lately by all the topologists that I know. I'm friends with a lot of people that do topology. If you're not familiar with topology, it's the study of shapes and how they change when you deform them in certain ways according to certain rules. And they always tell me all these things that they say are theorems. But I guess being a magician, or I don't know, I tend to come up with counterexamples to all the theorems that they formulate. And, you know, I'm starting to not buy the whole subject. So let me show you what I mean. For example, a topologist was trying to teach me about something that he called a linking number. And I said, what is that exactly? How do you define that? And he said, well, suppose you took 2 rubber bands like this. Okay, I hope you can see that. If you had 2 rubber bands, pieces of solid rubber, they couldn't go through each other because they're solid. And I said, well, no, of course they could. I just did it. And he said, no, it's called the linking number. And you see, if the bands are like this, in this particular configuration, they have a non-zero linking number. And it's a theorem in topology that because these are solid bands, that they can't just go through each other like that. But then, you know, I just disproved it, right? So I tried to read the proof. I didn't really understand it, but I think the whole thing is not really mathematically valid as far as I can tell. And then they were telling me about another fact, so-called fact of topology, which says that if you take a piece of rope like this, and you don't let go of the ends, there is no way to tie a knot in the piece of rope. And a topologist actually tried to show me a proof of this theorem, that it's impossible to tie a knot without letting go of the ends of a piece of rope. And again, I said, I don't believe that. That's completely bogus. Watch. And I picked the rope up like this, right? And I said, look, see, I tied a knot on a piece of rope and I never let go. And then my topologist friend said, oh, no. You just violated the hypotheses of the theorem. I forgot to tell you all the hypotheses. One of the hypotheses is you're not allowed to cross your arms. Okay, well, you didn't say that, so your proof is not valid. But okay, fine, topologist guy. I'll play by your rules. So I'm not allowed to do this, you say, right? So I picked up the rope this way. I said, I think I still have a counterexample to your theorem. So I went like this. And like that, and without letting go, I tied a knot in the piece of rope. So I think the moral of the story here is that you should take everything topologists say with a grain of salt, because when they say something's impossible, if you're a magician, nothing is impossible. Now, it's not just topology, though, that I tend to find counterexamples to. Also things in, for example, probability theory. Now, it's harder to give counterexamples in probability because most of probability is just about what usually happens or what's likely to happen. And so technically, you know, if something's very, very likely to happen, or let's say it's very unlikely to happen, it doesn't mean it's impossible. It just means it's very unlikely. But anyway, here's one of the things that I found suspicious. The claim was, it was about the expected number of cards you would have to deal until you got to an ace. Okay, so if there's a standard deck of 52 cards with 4 aces, how many cards would you expect to have to deal until the first ace came up? And now some people would say, well, there's 52 cards and 4 aces, and so on average it should be 13. Turns out, according to the probabilist, that's wrong. The answer is a little more interesting. The answer, as some of you may know, people are, I see, typing guesses into the chat. That's good. Feel free to guess what you think the answer is. I'm going to tell you in just a moment what the probability folks say. They say that the answer is 10.6. I don't know if anybody got that right. 10.6 cards on average. Now, where does that come from? So I'll show you the proof this time. This is, we're taking a tangent to go from the magic show briefly into a math lecture, as I'm wont to do sometimes. So here's the argument. It's a beautiful argument. It's really, really pretty. And if you subscribe to Peter Winkler's Puzzlers of the Week from the Museum of Math, then you may have actually seen this. This is one of the puzzlers he highlighted. But okay, so here's the idea. Suppose this line represents the deck from 1 to 52, and then there's 4 aces somewhere distributed randomly throughout. They don't have to be equally spaced, they're just randomly shuffled in. So then the idea is that this separates the deck into 5 parts, here, 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 and here, right? So there's 5 separate parts of the deck that the 4 aces break it into. And now the argument is that the expected size of each of these 5 parts is the same. So you would expect each of these 5 to be the same size. Now, if you believe that, then it follows that we've got, well, if you take away the 4 aces, then you've got 48 cards left, right? And then there's 5 spaces that they're divided into, 5 chambers. And so 48 divided by 5 is 9 3/5, right? So 9.6. So you would expect this right here to have 9.6 cards on average, and then you deal 1 more card for the ace, so that gives you +1 is 10.6. Now, some of you may have understood that. Some of you may be thinking, well, why would these all be the same size, though? I'm not convinced of that. There's an argument for that the probabilists will give you. Here's an argument I really like that appears to prove this. It's a symmetry argument. So what you do is you add in a 5th ace. I know that's not allowed in a game, but in our imagination, we can do whatever we want when we're mathematicians. So you add a 5th ace. Let's call it the ace of illusions. So you have the ace of clubs, hearts, spades, diamonds, and the ace of illusions. And those are randomly divided somehow around the circle. Now let's say this one right here is the ace of illusions. What we do, now it's clear by symmetry that if I form a circle and I mix in these 5 aces at random, then each of these 5 segments is expected to be of the same size because it's a completely symmetric situation. Right? None of these, this couldn't always be bigger than this one because you could rotate it and everything's rotationally symmetric. So these are expected to be the same size. But now what you can do is divide those 5 aces like this, then cut the circle here, remove that ace and straighten it out. Right? So you break the circle here, straighten it out, and now there's 4 aces. And we just said that this segment is the same expected size as this segment, which is the same as that. And it gives you the same distribution here. Okay, if you didn't understand that, it doesn't matter because I'm about to show you that it's probably not correct anyway. But that's the supposed elegant, beautiful argument that I've seen, and it seemed pretty convincing to me. But check this out. I mean, after all, the great thing about decks of cards is that we can actually run experiments, right? So I have here, I hope you can see this, a deck of cards, and there's 4 and only 4 aces, and I'll try to show you that. So there's 1 ace. There's a second ace. I hope you can see this. There's a third ace right there, and fourth ace is there, and no other aces. Can you all see that? Hopefully. All right, so 4 aces randomly in the deck, and just in case I had something set up or whatever, let's shuffle it a bit more. And here, I'll make some cuts as well. Like that. And now, random deck, the expected number of cards, supposedly 10.6. Let's see, there's, oh, you see, this time I got 1. That it came up in just 1. So see, it tends to be much less than 10.6 in my experience. We'll just put that ace back. Let me shuffle these again. Yeah, I just, somehow I don't really believe that whole 10.6 thing, because, let's try it again. All right, you see, it came up on 1 again. I don't know, something's fishy to me. Let's try cutting it again. We'll try cutting this way. And see, it's 1. I feel like the answer is much closer to 1 than to 10.6, at least, based on my own experience. I'll do it one more time, because, it's just probability theory. So we could just be having interesting luck here. You never know for sure. But I've done this a lot of times, and I feel like it always ends up, being basically 1. So I don't know. I don't know why that happens, but I'm just saying I kind of doubt that theorem too. But I don't have a counterexample or a disproof just yet. Okay, so that was a little introduction to the kind of stuff that I like to do in this environment. I like to just present magic tricks that involve either a math presentation or mathematical methods. I will be explaining some of the things that I do a little bit later. But first of all, I wanted to do an interactive trick with you all. So if we could, Scott, get a volunteer to raise their hand, someone that has a cell phone on them with a calculator on it. And then whoever you pick as a volunteer, we're going to spotlight them along with me. And I'm going to try to read their mind over Zoom. Hi, Kevin.
Hello. Would you like me to use my phone calculator or my much stronger scientific one?
Oh my goodness, you have like an actual calculator. I haven't seen one of those in years. Yeah, let's use that. Sure.
Cool. All right, let's go.
Okay, so here's what we're gonna do. I would like you to type in a random digit between 1 and 9. Mm-hmm. We're not gonna use 0 because we're gonna be multiplying things together. And if we ever use 0, it's gonna end up being 0. That is a theorem that I believe. Okay, so if you've typed in that random digit, hit times. Mm-hmm. Now type in another random digit.
Between 0 and 9, 1 and 9. Right.
1 and 9, yeah. And now hit times and do it again. Mm-hmm. And then keep doing it until you get a number that's pretty big. Maybe like, 10 digits or something like that.
Huh, okay.
So just keep multiplying, but don't do like, the same number every time. That's kind of boring. Make it something that would be like impossible to guess, okay? And tell me when you've gotten to a number that's, 10, 11, 12 digits, something like that.
All right, I got one. Okay.
Now, you're staring at a bunch of digits, randomly determined by you. I want you to just mentally circle one of those digits. Have you done that?
Okay.
Okay, now, you're gonna read all the digits that you didn't circle to me. Now, if you circled a 0, hopefully you didn't circle a 0 because that's a little confusing. If you circle 0, choose something else. But if you had circled a 0, then you would read all the other zeros, but not that one. Does that make sense?
Right, okay.
Okay, and so read them nice and slow to me. And then I'm gonna try to read your mind.
9, 1, 0. 9, 3, 3, 4, 4, 0.
Okay. And now take a look into the screen. I'm going to try to read your mind. I'm going to try to figure out the number that you circled in your own mind out of a bunch of random digits that you typed into the calculator yourself. And I can't see your screen, but I do. It's a little harder to read minds over Zoom than in person, but I think you circled a 3. Is that correct?
Oh, wow.
Now get it?
Yeah. Damn.
Thank you. Thank you. I will be actually explaining that trick later, and you'll all be able to go home and do that by the time that this show / lecture is over. So thanks very much, Kevin. We can give you a virtual round of applause. Okay, but I want to go on to another performance piece. The following thing I'm going to do is an original effect of mine. So I gave myself permission to teach it to you all. And it's about the phenomenon of crowdsourcing. But one of the things that really fascinates me is the wisdom of crowds. Now, if you don't know what I'm talking about, a famous example of this occurred in England in the fall of 1906. There was a regional fair, and a bunch of people gathered around and were asked to bet on the weight of an ox that was about to be slaughtered. And over 800 people participated in this little impromptu contest, and they were asked to guess. And a few of them were probably butchers or farmers or something, and may have had some knowledge, but most of them had no specialized knowledge of the situation at all. They were just guessing. Anyway, what happened was the actual weight of the ox was 1,197 pounds. And the average of the guesses of all of the people in the crowd was 1,198 pounds, off by 1. True, it's a true story. So what is their judgment was essentially perfect. So what is the moral of this? Well, what this little anecdote illustrates is that groups, under the right circumstances, groups of people can be remarkably intelligent, even if lots of the members, individual members of that group don't have any particular knowledge of the situation. And in today's world, taking advantage of this kind of phenomenon is known as crowdsourcing. So I want to do a little experiment to test these ideas for ourselves. And so we're going to play a game with 2 members of the audience here. And we're going to use crowdsourcing to try to predict the outcome of the game. All right, so first of all, do we have 2 players for the game? So we have Alex and Nevin. Perfect. Hi. So Alex, you'll be player 1, and Nevin, you'll be player 2. Okay, and I'm going to have you all make a prediction about who's going to win this game. We're just going to crowdsource this, because if I had made the prediction, you're like, oh, he's the magician. But you all are going to do it. So we have a poll. So which player will win the game? I promise I'm not manipulating this. This is Scott running this poll. So you all can vote on your own computers, and whatever gets more votes, that's who's going to win. So player number 1 is Alex, and player number 2 is Nevin. So give you 5 seconds to fill out this poll.
I'd say 1 is the winner.
1 is
the prediction.
Okay. All right. So Alex, player 1. Poll question number 2 was going to be predicting the spread, the point spread of this game. So Alex and Nevin are going to play a game. Each one will end up with a certain number of points, and it's usually a pretty close game. But your prediction is that Alex will win, and we want to know, though, if he's going to win by 1, 2, or 3 points. So if you could all vote on the point spread of either 1, 2, or 3, and I'll again have Scott just do the best he can to decide what the majority says. The important thing is I have no say in this myself. It's up to the moderator here to decide, and he didn't even know what we were going to do here. So Scott, what do you think? What is the expected point spread?
Matt, it looks like 3 is the winner of the prediction.
3. Okay, then we'll go with 3. So we're going to say that Alex is going to win by 3. So, and one more thing that I meant to tell you is I've got 2 envelopes. One says winner, one says loser. And Nevin, when I say loser, I don't mean it in like a personal way. It's just it's just a game. It's not a permanent label either. It's just for the duration of this game. So Alex is on my right, the way I'm seeing it. So I'll put Alex over here, Nevin over here, and now we're going to play a game. And I need to show you what we're playing with. We are playing this game with M&Ms. It's going to be played with M&Ms, but the colors that Alex and Nevin are playing with are inside the envelopes. Because if I tell them now which colors they're going for, then it sort of stops becoming a random thing. It becomes like they try to either make it work because they like me, or they try to screw me up because they don't like me. And either way is no good. So they don't know what colors they're playing for. But we're going to open up this bag of M&Ms, nothing in my hands. And we are going to play a game where I hope you can see these colors. Who should go first, by the way? Scott, you just choose. Should Alex or Nevin go first?
Nevin, why don't you go first?
Okay, that seems only fair. So Nevin, just name a color and I'll push it over towards the loser envelope.
Blue.
Blue, okay. So we push a blue over to there. And now Alex's turn. Which color would you like?
Yellow.
Yellow, okay. Very good. And Nevin, your turn.
Yellow.
Okay. Alex.
Red.
Red. Okay. And now, Nevin, let's do two at a time just to speed it up.
Blue and yellow.
Blue and yellow. You're hogging that. Alex.
Red and blue.
Red and blue. Or we've got almost all orange left and one red. So Nevin, what would you like? Do two more?
Red and orange.
Red and orange. Okay. And I guess, so that
Orange,
leaves Alex with orange, 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 orange. But since that went a little fast and you didn't realize we would run out of so many colors so quickly, if you want, I'll give you one chance to switch. Nevin, would you like to switch any of your colors for any of Alex's?
No.
Alex, would you like to switch any of your colors with any of Nevin's?
No. I mean, I would like to switch an orange for a blue.
An orange for a blue. Okay, so an orange goes over here and a blue goes over here. Are we good now? Nevin, I'll give you one last chance.
You're good.
We're good? Okay, so we'll stop there. Now that seemed pretty fair to me. I did everything exactly like you told me to, and you all made all the predictions. I didn't do anything here, but we're going to read out the predictions. So you guys said, or we're gonna look at the outcome now. There's two colors in here, and those will be Nevin's colors. Two colors in the winner envelope, those will be Alex's colors. And you all, with your crowdsourced wisdom, say that Alex is going to win by 3 points. Let's see. So in Nevin's, we have blue and yellow, both sides. And in Alex's, we have red and orange on both sides and nothing in the envelopes.
I shouldn't have traded orange for blue.
I know, right? But you did. And I think the crowd knew this because watch, blue and yellow, we have one, whoops, you can't see that. 1, 2, 3 points for Nevin. And red and orange, we have 1, 2, 3, 4, 5, 6 points for Alex. Alex wins 6-3. That is a point spread of exactly 3, which is what you all predicted, thus confirming my expectation that there is something to this theory about the wisdom of crowds. Thank you so much, Alex and Nevin, for participating. Thanks.
May I ask you a question?
Sure.
You know that there'd be more oranges and reds, so therefore you put orange and red in the winner envelope?
I will explain this trick in just about 10 minutes for you, and you'll learn exactly how it works, okay?
Okay, thank you.
So that's the nice thing here is this is all open source material. So, well, I hope you protect it yourselves because this is a trick that I'm proud of, but I will explain it to you all. I don't mean open source like go share it to everyone on the internet and say it's yours. Not that kind of open source. Okay, so I'm going to do one more thing, and then we will explain. Actually, you know what though? Let me switch the order up a little bit. So I'm going to actually explain some things, then we'll go back and do one more trick at the end. Okay, so that way, so I can see that everyone wants to learn a couple of these tricks. So let's go back to the calculator trick that I did, and I'll explain that one. And then I'll explain the crowdsource prediction I just did. And I'll do one more routine for you, excuse me. So the calculator trick. So what happens here is this. Just to recall what happened, I had my volunteer take out a calculator, type in a bunch of digits and just multiply them together until he got a pretty big number, like 10 or 11 digits. And then I had him mentally circle one of those digits, read the other digits back to me except that one, and I was able to tell him what number he circled in his mind. Now, how does this work? It's a combination of two principles, which is what I like about this trick. This is an old trick. I mean, Martin Gardner wrote about similar things, and many others have written about it, but I haven't been able to trace the source of this combination of ideas. So it's based on two things. One is the concept of digital roots, and the other is some probability theory mixed with a little number theory. Number theory is my specialty, what I was trained in as a doctoral student. So this has lots of interesting things. I said I don't believe in probability theory, but I actually do. So here's how it works. So let's say, I'll just make up a number now. Let's say that the digits that appear on the calculator are like this: 1, 2, 9, 8, 7, 4, 3, 1, 6. Okay, just a random example. And then the spectator mentally selects one of those numbers. Let's say they pick 8. Now here's the thing. If they really followed the instructions, then with very high probability, I know something interesting about this number. What I know about this number is that it will be a multiple of 9. Okay, now how do I know that? Again, it doesn't always work, but if it's 10 or 11 digits, then 90-something% of the time this will work. And so why is that? Well, if you multiply, and then we'll check in a minute if this random number I wrote down is or is not a multiple of 9, that's the concept of digital roots. But first, so how do I know that this number is going to be a multiple of 9? Well, if they ever type a 9 in that whole process of typing digits and then multiplying, then the end result will be a multiple of 9 by definition, I guess. But that's not the only way. They could also type a 3 and another 3 at any point, or a 3 and a 6. That will give us 18, which is a multiple of 9, or a 6 and a 6. So if they type 2 3s, 2 6s, a 3 and a 6, or 2 9s at any point in forming that 10-digit number, it will be a multiple of 9. And so I calculated the probability that this would work, and I choose enough digits to reach my confidence level. So if you want to be super confident, let them stop at a 15-digit number, and then you'll basically be sure. If you can take a little more risk, you can stop after 8 digits, and most of the time you'll be right. So you can actually set your tolerance. Okay, now, if this was really a multiple of 9, then the digital root would have to be 0. So what is the digital root? You add together all the digits, but anytime you go bigger than 9, you cast out 9s, which means you add the digits together that you have left. We're going to use a shorter number for the purposes of demonstration. Okay, this should be a multiple of 9. So let's say they mentally circled the 8 and they didn't read that. All we do is we calculate the digital root of what's left. So 7 plus 1 is 8, plus 2 is 10. That gives me 1 plus 0 is 1, plus 9 is still 1. Plus 7 is 8. 8 plus 2 is 10. 1 plus 0 is 1. So my digital root is 1. But remember, if we had included the missing digit, it would have to give us a 9, a multiple of 9. So the missing digit, if my digital root of everything else was 1, the missing digit must have been an 8. It's the complement. It's 9 minus whatever you get at the end. So I hope that made sense. It's hard to explain it upside down, and I confused myself, but I think that probably made sense. So that's how the trick works. So it's based on the number theory that shows that this digital root process works, and that you're going to get a multiple of 9 at the end with high probability, little probability theory, and then this mentalism. I make sure they don't circle a 0 because there could be ambiguity if there was a 0 versus 9. So I just I use that as an example, and I say, hopefully you didn't circle a 0 because that would be weird to put a circle around a 0, could be confusing. And then I have them change their mind to something else. Okay. All right, so that was a trick inspired by Martin Gardner. And now for the crowdsource prediction. Let me explain that. And yeah, I was asked a question about the colors. I will always set it up so that the winner gets the colors that there are more of than the other colors. And I'll explain this in just a minute. So we're going to use red and orange like we did for the sake of demonstration, but you can use whatever you want. Those go in the winner envelope, and the blue and yellow go in the loser envelope. And threw my M&M bag on the floor, but that's okay. I still have the M&Ms here. So here's what happens, right? I crowdsource the prediction. Who's going to win can be either player. I just give whichever player they say wins the winner envelope. The other one gets the loser envelope. And then I ask for the point spread. And if you want to make this even fancier, you can have a wider spread, but I use 1, 2, or 3 to keep things kind of simple. And if I'm doing this, nice thing is you can do this close up at a table for just one person or for a small group of people. And let them make the decisions, or you can do this. I've done this for a whole big audience, and you can have people raise their hands and have a judge on stage like Scott was doing to, say who got the most votes, but you don't make the decisions. So in this case, it was Kevin was the winner by 3 points. And it seems that all I did was open up a bag of M&Ms, dump them out, and play a fair game. Okay, but there's little more going on here than meets the eye. So one thing, let me tell you the math principle involved, and then I'll tell you the little bit of trickery involved, that sort of secretive magician stuff. And then I'll go back and I'll explain why the math works, okay? So here's the principle that's involved. The amazing math principle here, which is something I really love, is that if you play this game the way we did, the actual moves that they make, the actual choices don't matter. All that matters is the relative number of the different colors. So whatever color distribution I start with is going to determine the outcome of the game no matter what they do. Now that may seem counterintuitive. Hopefully it does seem counterintuitive. I'll explain in a little bit why that's the case. But just accept that for now. It still doesn't quite explain the trick, right? So I claim that I can set it so that I'll end up with whatever result I want, but I gave the audience a choice about different results. Well, this is set up so that whoever has the orange color is going to be the winner, first of all, the way I have this set up. So that's why I have the orange in the winner envelope. It actually doesn't matter who has the red, but I just put those together. Now, so whoever has the orange is going to win the game, but by how many? Well, in this case, with this distribution of M&Ms, it'll be by 3. But if I took away 2 of the M&Ms, 2 of the orange M&Ms, then Kevin would have won by 2 rather than 3. And if I take away 2 more of M&Ms, then I claim that Kevin will win the game by 1. And if I took away 2 more M&Ms, it would be a tie. Now, again, I'll explain the math behind that in a minute, but what's the trickery? How did I get these here? Well, there's 2 methods that I use depending on the performing situation. One method is sleight of hand. So you could actually, what you could do is start with 2 M&Ms in your left hand, 2 M&Ms in your right hand, and the rest in like a little bowl or in a bag that's been partially opened. And depending on what they say, I have to either dump these M&Ms in my pocket and get rid of them because That would be if the point spread is 1. If the point spread is 2, as I pick up the M&Ms, I'm just going to secretly add these 2 from my hand, and I'll hand it to the spectators. And if it was a point spread of 3, then I will, bring my hands together. Bring my hands together briefly to bring those 4 M&Ms together. Do that just kind of casually as I'm talking, and then reach in and add 4 M&Ms to the mix. So that's the sleight of hand way to do it. You can imagine other ways you could set that up as well. If you're not comfortable holding out M&Ms in your hands, but they don't melt in your hands. That's the great thing about M&Ms. They melt in your mouth. Anyway, back to the trick. But that's not what I did here. What I did was something possibly sneakier. I just took them out of a sealed bag that was in my pocket. But you see, in my pocket, I actually have a card box, and it had 3 packets of M&Ms in it. I had one that is going to be a point spread of 1, one that's a point spread of 2, one that's a point spread of 3, and I know which is which, and I've preloaded them. So what I did was I actually took 3 bags of M&Ms, opened them up very carefully so that you don't tear it and make it look like they were opened. I dump out the contents. I bought another bag of M&Ms just so I would have enough of all the colors I wanted. I loaded the distribution I need in here, and then I use a piece of double stick tape to seal it back. And then I mark it so that later on, if I have to come back to it, I can be sure I did it right. So I don't know if you could see, somehow M&Ms are made so that there are 3 dots in the corner. These kind of bags have 3 dots. So it's perfect. I just put a red, I color one of them red, and that's 1. And my 2, I color the middle, and 3 is there. So that way I can double check that I got the right one out of my pocket. And so then I can actually, it's totally clean. The audience makes all the predictions themselves. I take out a sealed bag of M&Ms, hand it to them. They can open it themselves, and I never touch anything. And then they make all of the moves themselves. I never touch anything. They can open up the envelopes themselves, and they can count the prediction, and it's right every single time. And I like the plot of talking about crowdsourcing, and that story I told is a true story from a book called The Wisdom of Crowds, and that's the first anecdote in the book. So I don't know, I enjoy the presentation and the effect, and then the method is pretty cool. So here's the explanation for why it works. It's easier to explain. Oh, and so, yeah, the idea is I have the same number of yellow, red, and blue, and then I have the same number of orange plus 2 more if I want a point spread of 1, 4 more if I want a point spread of 2, and 6 more if I want a point spread of 3. So the distribution I used here was 3, 3, 3, and 9. 9 of the orange, and that's what gives me point spread of 3. You just divide the difference by 2. Okay, but why does it work? All right, so let's explain with just 3 blue M&Ms and 3 yellow M&Ms to keep this nice and simple. It's the same with 4 colors, just it's harder to understand, which is good if you're the magician. You want it to be hard to backtrack. The effect is easy to understand, but the method is hard to backtrack. But let's do it with just 3 and 3. So, and I'm going to make this be a tie. So obviously, if Kevin had picked 3 and my other volunteer had picked 3, then it would be a tie. It would be 3-3. Okay, but then what if they had switched? What if Kevin had taken the blue one and my other volunteer had taken the yellow one? Now over here, and let's say this spectator's color was yellow. Now we have 2 yellows over here and 2 blues over here. So it's still a tie. Yellows and blues are still tied. And if I switched again, put a yellow here, blue here, now I have 1 yellow here, 1 blue here, they're still tied. No matter how I mix these up, as long as there's 3 and 3, there's always going to be as many blues over here as yellows over here. This is another principle that Martin Gardner wrote about. There's a nice paper of his where he talks about math principles that can be used in magic tricks, and he talks about a card trick based on this principle. And other magicians, including Bob Hummer, had card tricks based on this principle. It's the same principle that if you sort of pour water into wine and then the same amount of that mixture back into the water, you have the same amount of each. There's many puzzles and things based on this idea. But you know what others have realized in the context of card tricks, and I moved into more of a mentalism trick with objects that aren't cards, is that you can also imbalance it. So if you, if we now add, let's say 4 oranges, no, let's use 5. So 5 oranges and 3 yellows, and each player gets 4. So now orange wins by 1, right? Because we have 4 oranges and 3 yellows. So orange would win by 1. But if I switched an orange and a yellow, say, now it's 3 oranges and 2 yellows, but orange still wins by 1. And if I switch again, I have 2 oranges and 1 yellow. Orange still wins by 1. So no matter what, there will be 1 more orange here than there are yellows here. And that's because I have 2 more oranges altogether than I have yellows. And you can work out the algebra for this if you get the idea, and you'll see that, that this always works. And so I can actually arrange whatever point spread I want. And that's the trick that I call crowdsource prediction. Are there any questions, Scott, that people have asked?
Yes. So Silka, I think is how you say it, asked with reference to the first trick, what other number groups would work?
Oh, in the calculator trick?
Mm-hmm.
What other number groups would work? Well, I mean, I don't know, you know, casting out 9s works because we do things in base 10. That's sort of what makes it work. So if we did things in base 12, then you would use casting out 11s. I don't know if that was the answer, but you just need a lot of digits to make the probability very high that you'll end up with a multiple of 9.
Okay, and Wayne asks, sorry, yeah, Wayne asks a similar question. What happens if it's not a multiple of 9?
Right, so then it's not going to work. So that trick can fail. But that's also why I like it, because mathematicians tend to think in terms of algorithms and certainty. So if you do this, you know, it's clear there can't really be an algorithm that works in all cases for this trick, right? Because they're just typing random numbers. They could type anything. So it seems impossible, but that's what I like about it. So you have to be willing to tolerate some risk of failure. But I have a blog, by the way, where a lot of this stuff is talked about. And then I have a blog at Vanishing Ink Magic, which is called Mathemagical Themas. That's a play on words of Mathemagical Themas, which was Douglas Hofstadter's follow-up column to Martin Gardner's Mathematical Games, which it's an anagram of. So there's this sort of whole legacy in that thing. But anyway, Mathemagical Themas, Matt Baker, Vanishing Ink blog, and you'll find a detailed analysis of the calculator trick, including the exact probabilities if you have a certain number of digits that the spectator ends up with of failure. I don't remember it all off the top of my head.
Okay, we have a comment from Kay who says, back to the knot at the beginning. As a scout, I learned the middleman hitch that is done without using the ends of the rope. Okay.
Right. So yeah, I can explain the knot thing too very quickly. So this is something John Conway was very fond of doing. And if any of you saw my tribute to John Conway on one of these Zoom events, I think I did this, or maybe I did it in another context. But anyway, but this goes back to, I believe it's called the G.W. Hunter Puzzle Knot, and it's in the Tarbell course of magic, as well as some old books on rope tricks. So here you go. Here's how it works. I cheated. I did let go of the ends. You just didn't see it because it happens very quickly and in a blocked out way. So here's how it works. You, yeah, thanks. So you go around like this. Okay, so you take the knots and you hold them, you pinch them between your thumbs with maybe about 1 inch or 2 at the ends. You go around over your arm. Okay, and then you go away from you through that bottom loop. And then there's another little V at the top here, and you come back through that V. And so far, everything's fair. Okay, so far, I really haven't let go, but now I'm about to pull my hands back around, down and around, and I'm going to briefly let go with my left thumb. And then I regrip it, and it happens right there. Okay, so I'll do it again. So it happens in a split second. You let go and then regrip. And because of the knot is hanging over another piece of rope, it doesn't fall. And so you're able to quickly regrip. So check it out again. So you go over, through the bottom, and then back through that V at the top. And as you pull it back, I'm going to let go and regrip. And that's it. It happens in the blink of an eye.
We have a question from Andy. Sorry.
Yeah.
It says, can you provide the source of the Gardner paper you mentioned about math principles that can be used for magic tricks?
Yeah, it's in a book that I think was published by the, let's say, the Mathematical Association of America. I don't remember off the top of my head, but I tell you what, I know Andy actually, and I can send him the reference, but anyone that wants to learn more about any of the tricks I'm doing here, just email me. It's mbakermath@gmail.com or mbakermagic@gmail.com. They both work, depending on whether you want to address me as a mathematician or as a magician. And I'll be happy to answer questions about that.
Thank you, Matt. Very, very entertaining. Lots of fun, and fun to participate in too as well for me. Thank you, Matt. I'll stop the recording now.
Yeah, thanks so much, Scott. Thanks for helping out and moderating.